Okay, good morning, everyone. Good afternoon or good night for some of you. Thank you very much for participating in this new session of the online meetings of the Worldwide Energy Network, Distinguished Lectures Program of SERC. Today, we will have the presentation Photovoltaic System as Virtual Energy Storage for Frequency Support with Professor Yongheng from Zhejiang University in China. Professor Yongheng received the bachelor degree from Northwestern Polytechnic University in China in 2009 and the PhD degree from Aalborg University in Denmark in 2014. He spent a few months as a visiting scholar at Texas University in the United States, and since 2014, he has been with the Department of Energy Technology, where he became a tenured associate professor in 2018. He joined Zhejiang University in China in 2021, where he is currently a professor with the Institute of Power Electronics. His research is focused on the grid integration of photovoltaic systems and control of power converters, mainly the mechanisms and control of grid-forming systems. Professor Yongheng, thank you very much for participating in these seminars. And for the audience, you will be able to write your question here in the chat of the Zoom or in our YouTube channel. And after Professor Yongheng's presentation, you will be able to make some questions and the discussion. Yongheng.
Okay, thank you, Marco. So it's my honor to present this topic to you, even it's online, but that's nowadays becomes the popular way to share ideas and then share different topics. So as Marco has introduced, my name is Yongheng, and I'm working as a ZGU 100 professor at Zhejiang University, China. And yeah, in order to keep the streaming flow better, then I will just switch off the video in order to keep the bandwidth. Anyway, and today I'm going to present topic entitled Photovoltaic Systems as Virtual Energy Storage for Frequency Support. We can see that there are more and more renewable energies integration across the globe, including in Europe, in Asia, and also in South America. Yeah. A little bit information about myself, and it has been introduced by Marco, so I will just skip this part. And about the presentation today, first I'm going to introduce the background and the motivation why we wanted to do this control and this virtual energy storage operation of PV systems. Then my focus will be put on the virtual energy storage. What is the concept? Then how we can use the concept to provide frequency support or frequency regulations in future distributed power grid. Then at the end of this talk, then I will summarize the major points, and we can have some time to discuss. Yeah, as we all know, then the renewable has experienced quite a fast growth in the past 2 decades. This graph basically shows the past 20 years, the global renewable energy increase exponentially, including solar energy and wind energy, and also other like bioenergy, energy, thermal. As another point we can see here is that the sum of solar energy and wind has exceeds the total capacity of hydropower by the year of 2020. So we could imagine that in the future we will have even more renewable energy that is based on solar and wind. And in terms of the net total annual additions, we can also say that the renewable has experienced a fast growth in the past 20 years. And in a single year of 2020, there was more than 80% net capacity that was added by renewable, and the less than 20% that's non-renewable, which means that's conventional systems. Yeah. Okay. Yeah. Let's move on. And in terms of the solar PV, and we can see this also has been experienced a faster growth rate in the past 20 years. And by the end of 2020, the global installed solar PV capacity has reached more than 700 gigawatts. And in a single year of 2020, there was more than 120 gigawatts solar PV installed across the globe. And we can also compare the growth rate among different renewable energy technologies, including solar PV, wind, bioenergy, hydro, and also other renewable energy technologies. According to this diagram, we can see that PV has the fastest growth rate in the past a few years. And between 2018 to 2020, the growth rate, the average growth rate for solar PV was 22%. And in a single year of 2018, the growth rate is 33%. We could imagine that in the future, there will be even more solar PV installed across the globe. This is because the cost of solar PV technology is still declining. And there is also a demand to further lower the cost of solar PV energy. And this is an example from the US Department of Energy, and they have published this solar energy technologies office. They announced this Sunshine initiative, which means that by 2030, depending on the technologies or the applications of solar PV systems, then the levelized cost of energy has to be significantly lowered. For example, for residential PV applications, this is the year 2020. Then by 2030, the cost for the residential PV should be lower than 5 cents per kilowatt hour. And we can see that for utility scale applications, the target by 2020 was 6 cents per kilowatt hour, and this has been achieved in 2020, which means that in the future, the cost for solar PV, either it is a residential application or commercial applications or utility scale applications, cost will be even lower than we could imagine, that more PV system will installed across the globe. The other thing is that we have more PV systems. How to integrate PV system into the grid? This basically shows the general PV power conversion systems from the solar PV panels, which is a static converting systems or static generators, which convert solar irradiance then to the electricity through the power electronics. Then here, then the generation is based on photovoltaic effect, and the power generated by solar PV panels is highly dependent on the ambient conditions. Then in order to integrate into the power grid, we have to use power electronics to maximize energy productions and also to condition the power from solar PV panels. So which means power converters or power electronics are essential, and they are very important to realize the power transfer from solar PV to the grid. And as I mentioned, for solar PV systems, we have to maximize the energy production from solar PV panels, which is highly dependent on the environment. For example, the solar irradiance level and the ambient temperature. So supposing we have a cloudy day with faster running clouds, then we may experience some power outputs optically. If the maximum power point tracking works fine, then we would see that at the grid side, there will be a fluctuating power injection into the grid. So this is not expected or designed, especially when the penetration level is high, because it may violate the balance between the generation and the demand. Then the system may become unstable because of the unbalance between generation and demand. So in this case, then we have to really deal with challenges behind the high penetration of PV systems. For example, we may say overloading at peak power generation periods. This is an example reported by BBC News back to 2013. Then a part of the Northern Islands electricity grid was overloaded because that was a really sunny day. Then every PV generating unit was generating the peak power. So beyond the overloading issues, we may also see some challenges. For example, the equipment failures and demand and energy management issues and the systems protections. And also, as I mentioned, the power electronics are very important in the integration of solar PV systems. And because power electronics is static converting systems, then they don't have a rotating mass compared to synchronous generators. If we have more power electronics, the system's physical inertia is reducing. So this is an example studied by National Grid. They examined the synchronous inertia in their systems from 2010 to 2013. As you can see, then because of the continuous installation of power electronics based renewable systems, we can clearly see a reduction of synchronous inertia. So for synchronous inertia, it's an index of the system's stability or the system's capability to respond to disturbances like frequency events and voltage faults. So we have to keep the inertia high in order to maintain the stability of the entire system. So with that, then we are having increasingly stringent demands on PV systems. So for PV systems ranging from several kilowatts to even a few megawatts power level, they have to comply with much tougher requirements than ever before. So this is a combination of standard PV features and also advanced demands for a grid-friendly integration of PV systems. For example, like the flexible power control, reactive power control, frequency regulation, etc. There are increasing demands for PV systems to keep the system stability. So with that, then for PV systems, so we are not expecting it is just a simple generator, but PV systems should be more active in grid regulations, which means they should not only just provide maximum power point tracking, but they need to flexibly regulate their active power. For example, like a constant power generation control, delta power control, also referred to as power reserve control, and also this power ramp rate control, because this is related to the system frequency. If you have a fast power change rate, then you may see that the frequency will also change fast. So that's also challenges the system stability. So with that, then we need to have this flexible power control, or what we call it virtual energy storage systems, because we didn't actually use energy storage. We try to operate the systems with certain amount of power reserve in order to provide frequency support, like you are using an energy storage system to provide the frequency support. So in terms of PV system configurations, here in these slides basically summarize the general configurations of PV system depending on their power level. For example, PV module converters, PV string converters, and also multi-string or central PV inverters. And in terms of control of PV systems, this slide basically shows the general control structure of PV systems. Because the power converters are the only controllable units in the entire systems, then we have to implement all the control demands or the control functions in the power converters. Fortunately, we can achieve almost all the demands by control by controlling the PV inverters. For example, the basic control, the grid support, and the active power control. So today in the following slides, I will introduce this flexible active power control. Also, we call it virtual energy storage controls for PV system to provide grid support, more specifically the frequency support. So in terms of active power control, of course, there are various ways to achieve so. For example, the most straightforward way is to integrate energy storage, physical energy storage, in the systems. Then this is the most effective and the flexible way, but it increases the cost and also the control complexity, because in addition to the control of the PV converters, you also have to control the storage devices by properly charging and discharging the energy storage units. And the other thing is that for battery storage systems or other energy storage systems, the lifetime is still limited, even though the technology is improving. But at current stage, the entire lifetime will be reduced if we integrate energy storage system in the PV units. Yeah, and another solution is we can consider this multiple units systems structure. Then we can flexibly switching in and out some of the units to achieve the power regulation. But of course, this is not the most flexible way because it's limited by the configuration, and the control is complicated, and it's depending on the communication, and if you switch in and out may challenge the entire operation of the systems in terms of stability. And the other thing is this is a unidirection solution, which means if you wanted to provide more power to the grid, this is not possible. And the last solution, we call it a flexible power point tracking solution. This does not require hardware modification, which means it is universal and easy to implement to all PV systems. The basic concept is that we moved operating point from the conventional maximum power point tracking mode to this non-maximum power point tracking mode in order to achieve the active power regulation to operate the system as a virtual energy storage units. So this slide further shows how we control the PV units as a virtual energy storage systems. And in the conventional way, we operate at the maximum power point, but in this virtual energy storage operation, we control it at the flexible power point with a certain amount of reserve power, which means if you further reduce the operating point, for example, at this point, then you are charging the batteries virtually. If you move the operating point towards the maximum power point, then you are discharging the batteries. So in this way, you are sort of operating your PV units as a virtual energy storage system. So with this concept, we developed this constant power generation control, which is also referred to as power limiting control. There are also three possibilities to limit the power generated by PV systems. For example, the direct power control, the current limiting scheme, and also the modified maximum power point algorithm. So because of due to time limit, so I will just skip those control details. I will directly go to the next virtual energy operation modes, what we call it power reserve control. So why we need this power reserve control? We consider the grid stability, and due to frequency excursion, if we have this fast fluctuate power injected into grid, then the frequency may go excursion because of the dependence of frequency and active power. But of course, because of this dependence, then we can regulate the frequency by control the active power from the generating units. So we can still implement this power reserve control with this virtual energy storage operation, then in this case, the power should be reserved, and in the case of needed, then we can release the power to support the frequency of the grid. So in this case, then the power limit is not a constant value. It is depending on the available power in the PV system. So this basically illustrates the idea of this power reserve control, how it can be linked to the energy storage system operation. When the system's operating at the flexible power point, then which means then your PV system is storing some amount of energy. So when you when your grid is under frequency events, then you can release this reserved power to support the grid frequency, which means you are discharging the batteries or the energy storage system of your PV system. So to achieve power reserve control, there are also some challenging issues to be addressed. For example, then how we can measure the available power of the systems. You can install solar irradiance measurement sensors, or you can use artificial intelligence techniques to predict the available power, or you can apply the curve fitting methods to sort of also predict the available power in the systems. So those above solutions basically either they increase the overall cost or the complexity of the systems, or they are model dependent, which means along with the model degradation or the PV module degradation, then the model may not work perfectly. So with that, then we propose two methods. One is we call it master-slave power reserve control. The other one we call it sensorless power reserve control strategy. So for the master-slave control strategies, which means some of the PV units are operating as master, which means we use this master units to measure the available power in the systems. Then the rest of the PV units are operating as a slave mode, which means then they are reserving some amount of power. Then what we see at the grid side is the PV systems with a certain amount of power reserve. So this is the concept of the master slave control. So we demonstrate these control strategies on two stream PV systems with a power reserve amount of 200 watts. As you can see, then for a clear day and also a cloudy day, PV1 is operating at the maximum power point tracking mode, and PV2 is operating as the power reserve. Then we can reserve the required amount of power in the PV systems, as shown in this figure. For clear day and also cloudy day, we can sort of achieve the power reserve. And for the sensorless power reserve control, we explain this control strategy on a two-stage PV systems with capacitors. So the basic idea is to routinely operate the PV systems at the maximum power point. Then we measure the available power. Then we quickly jump back to the power reserve control mode. Then in this way, sort of, then we can achieve the power reserve of the entire PV systems. So this further shows the operating block diagram of the PV systems. Then we first operate the PV systems at the maximum power point. Then we measure the available power, then which is subtracted by the power reserve. Then we update the power limit, which means then you move your PV systems from the maximum power point to the flexible power point. Then you can achieve the power reserve operation. But this has some issues. For example, even you operate the PV system at in a very short period at the maximum power point, but you are still expecting some peak power in the systems. Then this has to be stored somewhere in the systems. Then what we have done is we store this excessive energy in the DC link capacitor, then we sort of allow the PV system to increase the DC link voltage to store this energy. Then what we see at the grid side is more smooth power injection with a certain amount of power reserve. Then this figure shows the entire control block diagram of the systems, how we process the excessive energy at the DC link capacitor. This slide shows the some experimental results of the systems under constant operating conditions. Then we have this available power and the output to the grid, and we reserve the power of 500 watts. As you can see, we can achieve the power reserve. And as I mentioned, because we need to store this excessive energy, so our PV DC link voltage is increasing to store this excessive energy. And for changing environment, we can also achieve the power reserve of 500 watts, as shown in this figure. And yeah, as I have mentioned, we can use PV system to operate as virtual energy storage to sort of provide energy or to store energy in the operation in order to provide inertia or frequency damping in the systems. So as further illustrated in this diagram, if you are operating this your PV system above the power reserve point, then you are sort of releasing energy to the grid. If you further lower the power reserve operating point, then you are sort of store energy in the systems, which means you can deal with over frequency issue in the systems. Or if you want to release the energy, then you can sort of operate in this mode, then to address the under frequency issue. And the other thing is then in order to provide a full range of frequency regulation, then we need to coordinate the inertia provision by your PV systems and also the frequency damping by your PV systems. So the inertia is in proportion to the derivative of the frequency, while the frequency damping is in proportion to the frequency deviation. So we have to coordinate the power reserve in order to make it an optimal trade-off between the inertia and also the frequency damping. So in terms of virtual inertia control, we did some experimental tests when we have the power reserve or when we operate our PV system as virtual energy storage. Then we use this stored energy to provide virtual inertia. So this is the PV system without virtual inertia control, and this is the result with virtual inertia control. When we compare, if we adopt this stored energy, virtual energy to provide virtual inertia, we can see then we improve the rate of change of frequency of your PV systems, and also we can improve the performance in terms of frequency nadir when there is a disturbance in the systems. Overall, when we use this virtual inertia control, we can improve the frequency quality of the systems. The other thing is we can also use the internal storage to provide virtual inertia, because actually, if you wanted to provide inertia to the system, you have to use some energy storage to provide the inertia or to release the energy to the systems. Since we are using a lot of voltage source converters, then we have many DC capacitors in the converters, then we can use the DC capacitors to provide virtual inertia. So this is a universal solution, and because actually it is using the physical storage, which means here is DC link capacitors, and but it can only provide limited inertia due to stability concern. Anyway, when we use the DC link capacitor to provide inertia, we can sort of emulate the inertia by comparing the power equation with the synchronous generators power equation as shown here. Then we can see that the inertia from the DC link is related to the DC link voltage and also the control or the inertia gain you can provide it in the system. So we did a comparison on the different parameters. Then this is the emulated inertia. Either we are using a virtual synchronous generator or we use the inertia from the DC link capacitor. As you can see, we can emulate the same inertia by using the DC link capacitor, but it is very limited considering the entire stability of the system as shown in this figure. If you increase the gain, then you have stability issue in the system. So the last part related to today's talk is flexible frequency support from PV systems. Then we have to coordinate the inertial emulation and the frequency damping. This is the important index or indices for frequency response in power system. As you can see, there are two stages: primary frequency control and secondary control. So for primary frequency control, we care the frequency nadir, we care the rate of change of frequency, and for the secondary frequency control, then we are more concerned about the steady frequency in the systems after we apply the secondary frequency control. So there are also some requirements related to this frequency quality in the power grid. For example, in the northern European grid, then your system has to achieve this rate of change of frequency withstanding capability of ±2.5 per second. And then to improve the frequency quality, then we can optimize the utilization of power reserve, which means the virtual energy storage of the systems. And then also we can adaptively adjust the inertia constant and the damping gain in order to coordinate or optimize the operation. Then we did a basic study and how the inertia constant will affect the frequency quality and how the damping gain will affect the frequency quality. Then we can conclude that we expect a large inertia constant before the nadir, and we expect a larger damping gain after the frequency nadir. Then we proposed a control strategy, and we also compared with the state-of-the-art strategy. For example, fix the damping gain and fix the inertia constant, and also the system without frequency control as compared in this figure. We can conclude that with the proposed coordinated operation, then the system performed well in reducing the root off and the instantaneous frequency deviation. And then we can optimize utilize the power reserve to reduce the steady state frequency deviation as compared in this table. So to summarize today's talk, then we know that PV is still a booming area. Then the large integration of power electronics PV systems will challenge the power grid. And then we have to develop advanced control strategies. And the virtual energy storage control, for example, including this power limiting control, power reserve control, is a cost-effective solution to frequency stability. And we can further develop other advanced control strategies like at the system scale, then to further enable the manageability of the entire PV system. So with that, I will conclude today's presentation. Basically, the materials have been summarized in those two books. And if you are interested, you can refer to the two books. Oh, last one, and I would like to acknowledge my professor, Fred Blobia, my mentor, who is a professor at Aalborg University, and my former students, Dr. Aria Semavanic, who is now an assistant professor at Aalborg University, Dr. Chaupen, who is now a research fellow at Sichuan University, And most of this research is was supported by EU projects through the solar area net, and the local funding agency was Energinet.dk in Denmark. So with that, thank you all for your attention. So I did this a bit longer than expected. Thank you.
Thank you very, very much, Professor Yang. Very interesting and timely presentation, and as mentioned before, for the Chilean context. As you know, we are facing high penetration of PV systems, so this type of approaches are quite important. We have one question from the audience. I will, from Shini. The question is how to select which are master PV and slave PV. Any control scheme?
No, this is we did this in a very simple way. So because in our study, we did first did this study in the lab, and which means we use 2 PV units, and we assume that the 2 PV units have the same parameters in terms of power rating, and all the parameters are the same. Then we can select either one as the master and the other one as the slave. So in practice, what we can do is we consider, for example, a large PV plant. Then we can select, for example, the 4 corners plus the PV units in the middle as the master in order to average the arrow between different units. So this is what we can do in practice. And actually, this has been done by National Renewable Energy Laboratories. I think it was in 2019 or some time. They are doing the same as what we have done in this control strategy. Yeah.
Okay, thank you very much. A question from my side: if you can connect your presentation with the discussion of grid forming and grid following inverters, so we can, in fact, the whole development you need in the industry to incorporate this type of approaches. This will be very clarifying for the audience.
Yeah. So I think the first point I would like to clarify is that the control strategy we are proposing, or I have presented in today's talk, is not a grid forming control strategy. It is still for the grid following control, because we develop these control strategies based on the grid following control technologies. Of course, then if we wanted to completely move the power grid or move the power system towards 100 power electronics based systems, then we need to change from grid following to grid forming. And in that case, our control strategies can be easily adapted to the grid forming control mode in the future 100% power electronics or renewable based power systems.
And the DC condenser is part of the hardware that need to be included as part of the design of the inverter, or you can manage this independently?
You mean the DC capacitor, right?
Yes, the DC capacitor.
If it is for example, for the sensorless control strategies, then it has been designed together with the converters, because that's related to the stabilities. But of course, then if we sort of completely change the control structure, moving from the grid following to the grid forming mode, then for example, using this voltage oscillator control and also this virtual synchronous generator control, and also droop control, probably the design of the capacitors can be another story, because you need to look at first at the local converter side to maintain the stability of the converter, but also seeing from the system scale, then how you maintain the system level stability. I think that will be a kind of combination between the two.
Okay, related with the previous question, but I think it's good to clarify from Álvaro Morales. The question is, can grid following control strategy offer this frequency support?
Yeah, to my best knowledge, I think yes. The answer is yes. The grid forming control technologies can provide such support, because why we do this grid forming control strategies, because we want to emulate our converters to be synchronous generators. Then we can use, because for synchronous generators, it can provide frequency support and also other capabilities. Then we use grid forming control strategies. We can also provide such technology, such support.
Great. And from Carlos Salgado, congratulations, very interesting presentation. In the event of a short circuit fault due to the low inertia, it is necessary to accompany other systems such as flywheel, pump hydro, I mean, or super caps, since the rock-off is very unstable?
I think that to answer that question, of course, if your system has like a synchronous condenser, then it will be easier for the entire power electronics-based or inverter-based resources to ride through the short circuit fault. Otherwise, then your converters need to ride through this fault, because there are some strategies already available to ride through short circuit faults in the power grid. And of course, if you have synchronous condenser, you can easily help your system to maintain the stability. But of course, we can use this ride through strategies for inverter-based resources also to ride through the short circuit faults.
Okay, thank you. También, si alguien quiere hacer una pregunta en castellano, lo puede hacer y hacemos la traducción acá y tomar la palabra o escribirla. I am asking if there is any question in Spanish language, so we can translate and make it. Marco, any additional question from your side?
No, from my side. Everything was very clear and very interesting topic, which is very, very interesting for the situation right now in Chile and the rest of the South American countries. Thank you very much, Yongheng, for your presentation.
Yes, Professor Yang, you know what we are doing. Some professors in Chile are studying. Unfortunately, they are not connected. They use the derating approach to simulate the with good forecasting, as mentioned in one of your approaches. You can prepare for some specific time periods to derate our photovoltaics to be prepared to be able to support frequency in the case of a failure, of a contingency. And this is the type of studies, and the results are very impressive, that with a low economic impact, you really can improve the support. And of course, the discussion is how to deal with the current inverter technologies, because it's clear you can switch from MPPT mode to a fixed power injection in the derated mode. But it's not the same, as mentioned by you, which is much more flexible to deal with the different cases. But please, if you want to comment on that.
I completely agree, because recently I'm also doing a project and trying to sort of making our PV system really like a synchronous generator. Because in the past, what we have done is really just to emulate the behaviors of a synchronous generator. But for PV systems, it lacks internal storage or the rotating mass that's physically an issue for PV systems, then how we can sort of make the PV system to be like a virtual inertia, seeing from a hardware perspective and also seeing from the software perspective. So this is something I think at least for inverter-based resources should be a way to go in order to improve or to increase the penetration of inverter-based resources.
Great. Thank you very much for your time. I hope this is a starting point for future cooperation. All the people who attend will offer this presentation they can contact you. The contact with Aalborg is also very interesting as one of the main centers in the world working in this area. So we are very happy to open this opportunity with you and with the local scientific community. Thank you very much again for your presentation, and I hope to see you very soon.
Yeah, thank you, Rodrigo, and also thank you, Marco. Thank you, everyone. So yeah, thanks a lot.
Bye-bye. Bye-bye. Muchas gracias a todos por
Thank you very much, and we invite you for the next session in the next 2 weeks. Thank you, Yongheng.
Ciao, ciao.
Bye-bye.
Bye-bye.